Good day, viewers. So today we continue with the topic we started last time, vector and vector addition. And before we continue, I would like to do a recap of what those things that were taught last time. Talked about vector, scalar quantities. Also talked about vector addition, because we know the scalar quantities just require a normal or the ordinary arithmetic processes. But we're talking about the vector, excuse me, I'm talking about the vector itself, the vector quantities. Their addition is in a kind of geometric process, and not just like the scalar quantities. Just like when you have a vector and vector addition. That's when you have like mass. Mass is a scalar quantity. You can have 5 kilogram plus 3 kilogram. It will definitely give you 8 kilogram. That is just another arithmetic. But we are talking about in both magnitude and direction. Unlike the scalar quantities. Scalar quantities are quantities with just only magnitude. An example like this 5 kilogram is a quantity. Is a magnitude, just in mass, in kilogram. I'm talking about length of a distance. Distance. Distance is also what is a magnitude or a scalar quantity. Yeah, we also talked about the magnitude of a vector. Magnitude of a vector we can also see a magnitude of a vector as a scalar. And when you have magnitude of A, the symbol is this. Can give us a vector. That's the symbol for vector. Arrow above the letter, and the italicized letter, this represents a magnitude of a vector. A magnitude of a vector also you can classify. I can just say it is a scalar. Now we talked about that one, and we also talked about equality of two vectors. Equality of two vectors. When you have vector here, okay, this represents is an example of vector quantity. That's when you have, and that a vector is representing displacement, starting from this point, and this is direction. This is the tail of the arrow. This is the head of the arrow, and we also have another vector too, the same direction and the same magnitude. That's called vector B. Now, vector A and vector B, we can say they are two vectors that are equal, or we call it equality of two vectors. Vector A and vector B. They are equal for having the same magnitude. Next example, this is 3 meter, and this is also 3 meter, at the same direction. They're facing the same direction, facing upward. So we can say these two vectors are equal, or we call it what? Equality of two vectors. We call it equality of two vectors. Right. And also talked about antiparallel vectors. Yes, and before I move to that, between vector A and vector B, we say they are equal because both of them have they have the same magnitude and the same direction, and both of them are parallel, faces the same direction. Vector A and vector B are parallel. We can also call them what? Okay, two parallel vectors. And because they have the same magnitude and the same direction, we call them equal. We call them equality. They are equal. They have equalities of vectors. They are equalities of vectors. And antiparallel vectors is okay. I think okay. Antiparallel vectors. It can have a case like when you have vector here. Yeah, this magnitude of 5 meters, and we have vector B facing downward. And it's also 5 meters. These two vectors, they are equal. They have the same magnitude, but they're in opposite direction. So this kind of vectors, we call them antiparallel two vectors. We call them what? Antiparallel vectors. They have the same magnitude, but in opposite direction. We talked about that last week, and so it shows that vector A equals to minus vector B, because here we can put negative there. Vector A equals to what? Minus negative vector B. We talked about that one last week, and we also talked about I show you a magnitude of a vector, what it represents when you have a vector. So let's come up here. Yeah, we have the arrow has to be on top. So this represents what? A magnitude of a vector. You have two vertical bars, enclosing the vector. That represents a magnitude of a vector. And we also last week also we added this too. Under the vector addition, we make use of scale diagram. Scale diagram. Scale diagram. Scale diagram. That scale diagram is make use of arrow. Make use of arrow. One a vector. Two vectors. Supposing two vectors. Two vectors. Talking about displacement. Now that going. We have vector A and we have vector B. And for us to have the addition of the two vectors, because when you have a vector like this, we have vector A in this way, and another vector B. Second one. Now, this vector B. This is what we call scale diagram. Now, the position of vector A from its tail arrow to through vector B to its position. This position, the arrowhead of vector B. So if I have to check what the displacement from this point, let's call this point 1, P1, and this one point 2, P2. Now, from point P1 to point P2. We can call it resultant vector or vector addition, because the addition of vector A and vector B will definitely give us the vector from point 1 to point P1 to point P2. And don't forget that displacement is a change of position of an object from point P1 to point P2. So definitely, when we add vector A to vector and vector B together, it's going to give us the change in this displacement from P1 to P2. So the addition of vector A and vector B will give us the vector. It give us a resultant vector, which let's name it a R, vector R. So that will give us what R, vector R. So we talked about that too. And other things too, we using a scale diagram. When you have 3D vectors and they are arranged together in using scale diagram, the addition of all the vectors, the 3D vector, will give us the resultant vectors from one point to another point. Okay, for better understanding, exactly, we are having a point B, the displacement from point P1 to P2. This is a displacement. And we have several vectors within this position. Like we have this form, we have another one this way, we have another like this way, we have another to this point, excuse me, okay, yeah, to point P. So we have, so let's name this one vector A, vector B, vector C, vector D. Now the resultant vector, or the vector addition in this point from point point P1 to point P2. The displacement between P1 to P2 will now give us what the total addition of the vectors within the 2 points. So let's call this one R. The displacement. Displacement is a vector, so we can represent it with R. So we can have a vector R, which is the displacement between P1 to P2, will give us the resultant vectors of the following vectors. That's all. Now we also talked about, next one we talked about components of vectors. Components of vector. Now these aspects, we have, if we are to make use of a rectangular coordinate system, we'll be able to get a component of the vector. And that rectangular coordinate, we also call it Cartesian coordinate. Cartesian coordinate system of axis. And that really help us to know the components of vectors. So we talked about that. I'm just trying to do a recap. Now, components of a vector using rectangular coordinate or rectangular, also call it Cartesian coordinate. And it's 16 of axis. Okay, and it's like we have this. We have y axis, which is vertical axis, and we have the x axis. And except that we have a vector here. It's called the vector C. Vector C. Now, and from previous class we had that the addition of two vectors will give us adjacent of vectors, as I said. So when let's say we have a vector along x direction. Let's call it C x vector along x direction. We also have a vector along y direction. Therefore, we can set this. Okay, let's make it rectangular. Yeah. So therefore, we have this vector now C. Vector C will give us vector C along x-axis plus vector C along y-axis. And don't forget that we can also call x-axis horizontal, and we can call it y-axis vertical. And now, and once we have a vector along x-axis, so we call it vector C. Just this one. This is a vector along x-axis. And for us to make use of that value, we need to get what? We need to, we need to get the magnitude of that vector along x-axis. So we can now call vector C along x-axis. So the magnitude will be given to us as x and cx for better understanding, so that when we want to do some calculation with it, maybe to do it easily. Because vector C along x-axis, we can call the magnitude of it can be given to us as cx. Okay, and for magnitude of vector C along y-axis, it's given to us as so. Let's use small letter cy. I think that will give us able to differentiate it from cy and that of okay. So this we have cx. So therefore we can have this and that of the magnitude, the resultant key was this. So give us C, similar to C. So therefore, the components of vector in a Cartesian coordinate system given to us as like Cx, this is Cx, and Cy. Cx and Cy are components of vector. In a rectangular or Cartesian coordinate system of axes. So with that, and let's go back to the diagram. See that move back to the diagram above. See that at a particular way, I also talked about this last week, that an angle between them, this angle. So we discussed about that one, and for us to now, okay. So that's the angle now. And now that we've learned that Cx and Cy are components of vector, and for us to now know what for us to now relate that the component with the angle between what the vectors. So we work it this way. Now I'm just now going to make use of trigonometry functions, the cos theta, sin theta, straight away, and from the elementary or the high school knowledge about this called vertical components, the horizontal components. You know, when you have a vector,